Hi all, and welcome to the third lecture of the deep learning course. Today we're going to discuss about deep learning optimizations. More specifically, today we're going to study some advanced optimizers. We saw last time stochastic gradient descent, so today we're going to see some more optimizers out there. We're going to discuss about initialization and how important it is when training our neural networks. We're going to study a bit normalization and some of the most important methods out there. We're going to also study regularization so that we make sure that our neural networks don't overfit or if they do, we minimize the extent of it. And in the end, we're going to study how we can tune our hyperparameters. As a brief recap, we saw in the last lecture that the main algorithm for optimizing your networks is basically stochastic gradient descent, which is a simple algorithm. So given our current parameter vector, we are making a change, an update in the direction of the negative gradient after we rescale it by learning rate. Now, the landscape of the neural network loss function is actually very non-convex with lots of optima, minima, and actually very many types of pathologies, as we'll see today. So in general, it's not an easy task to actually optimize a neural network, and although stochastic gradient descent does a pretty good job, sometimes something more sophisticated is required. So what are the challenges in optimization? For one, we often have ill conditioning, which means that quite often, even if we do have a stroke gradient, we actually might get worse loss values after the update. What is quite obvious is that since gradient-based learning is a local optimization strategy, we are susceptible to local minima. There are various pathologies and pathological curvatures like plateaus and cliffs and others. We also have vanishing and exploding gradients as well as long-term dependencies, but these two last points we're going to discuss in a later lecture. So what do I mean by ill conditioning? We can generally understand and analyze possible behaviors of our neural network and its loss function thereof by studying its Taylor expansion. So if we go up to the second order Taylor terms, after analyzing the loss function, we obtain here the 0th degree, here the first Taylor term, and here is the second Taylor term. So the 0th term has no dependency of the gradient. The first Taylor term has depends on the first order derivative here, g. Whereas the second term depends on the Hessian, which is the second order derivative of our function. Now, let's say that given our Taylor expansion of our loss function, we perform an update around our previous parameter location W prime towards the negative gradient after rescaling it a bit, with a very small number. If we replace this guy in the loss function, we obtain that basically our new loss is going to be equal to L of W prime. So this is basically the 0th order term minus the G transpose times G. So basically this amounts to the inner product of the gradient with itself, the norm of the gradient, rescaled by epsilon, plus the gradient times the Hessian times the gradient. Now, why is this interesting? It could happen that even if G is strong, as in it's not having very small numbers in its dimensions, still this second order term is higher than the first order term. That would yield a loss function which is actually higher than the original one before the update. This means that in this case the loss goes worse and we're actually unlearning. So this case of ill-conditioning can actually be problematic, right? Of course, local minima, we sort of discussed this the previous time. Stochasticity alone is not always a panacea. We cannot resort or rely on stochasticity alone so that we avoid local minima. And a simple example is in these two pictures. So here, as we saw in the previous lecture, indeed the stochasticity, adding some noise to the gradient, might allow us to actually jump over a local minimum. However, in this case, this particular case, the gradient is still stuck on the same local minimum, just because, in the right of our current position, we're having a much flatter region. So, in general, as we discussed the other time, it's very hard to get a very good grasp of the geometry of the neural network loss landscape beyond our local neighborhood. Whereas these are nice 2D visualizations that give us a global overview of how the loss surface looks like, in reality we have a bunch of numbers in an extremely high dimensional space, and we have to make do, right? And our best hope is to actually just solve the problem. We have to do a good optimization, and if we do a good optimization, it means that we are actually discovering better minima. Ravines are types of pathological. Another problem that we face with neural network landscapes is pathological curvatures, pathological geometries, local geometries in our loss surface. Ravines is actually a very frequent phenomenon. A ravine is actually such a shape here where you've got great steepness in one direction and flatness in another. And maybe in this picture it's easier to motivate. So in this picture we see that let's say we are at point A. If we were to take the gradient, it would be somewhere like it would be somewhere diagonal like that, and no, that's not again correct. It would be something like that, and it would be like this because you've got a large gradient along this direction, and you've got a smaller gradient along this direction, right? And this makes sense because along this direction we've got great steepness, whereas along this direction we've got basically a very smooth transition. Now, why is that a problem? Because the large gradient here tells the optimizer that the update should actually go towards that direction, and after that update, when we are at this location, let's use a different color here. We're at this location, then the optimizer will receive the opposite gradient for an update. So what happens in the end is that we're just doing a zigzag that makes training much slower. What we ideally want is to maintain this direction of the gradient, which is actually a smaller component. Another pathological curvature that we often have to address are plateaus or flat areas. So in flat areas there are almost zero gradients, right? So here there are very, very small gradient updates that we can compute, which means then that our learning is actually going to be very, very slow. That said, if we are in a local minimum, which is basically a flat area, a plateau, this allows for great generalization. That is quite intuitive. So if we have, let's say this is our 1D parameter here, and this is the loss, and then we've got this very flat training area, training surface, and then let's say we've got a different color for our test surface. So because of the slight domain shift, we've got a new test, a new sample of our data points. So it's going to be slightly shifted, let's say like this. So for our training set, our optimal solution would be somewhere here, right? Now, because this is a flat area, most likely also for the test data, that's going to be a flat area, and we're going to end up in this location here, right? So exactly because of this flatness, we're not going to have very abrupt differences between the training and the test domain. Now, if we were to have a much sharper minimum, so let's say that now this would be our training set, and then our test set could be test set surface could be would be slightly to the right. If we were to now check our best minimum here according to the training set, that would be go very high, actually would generate very high test loss. So flat areas are actually quite good when it comes to generalization. However, if the flat area is not a local optimum, like a decent local optimum, it is actually bad because it sort of slows down training. Another problem that of course is connected with flat areas is when we've got flat areas in some part of the space and a very steep minima next to it. When combining these two geometries, this becomes very challenging, and the problem is that because we've got very flat areas, it's very hard for us to discover the location of these steep minima if we can even say that we do have some minima around. How can we even find them, So in general, because as we see, quite often we have different types of behaviors, different types of surfaces and geometries in different directions in the space, right? So in this direction, you've got very steep gradients, very strong gradients, very steep surfaces, so very strong gradients. Whereas in this direction, we've got very smooth transitions, so small gradients. An idea is that if we were to use the second order derivative, the curvature, so basically the rate of change of the first order derivative, the acceleration, how fast does our gradient change, that can help us adapt each dimension such that if there is too much change, then it gets slower, we slow it down, and on the other hand, when we've got very slow change, we try to speed it up. And in that case, we can adapt the learning parameter by applying the inverse Hessian on the gradient. So the inverse Hessian is basically the inverse of, you can think of it as the inverse of the partial derivatives. So if my second order partial derivative is very high, then the learning rate becomes smaller, and the other way around. Now, some more intuition perhaps. In this example here, A, we have, in both cases A and B, we have exactly the same first order derivative, right? If we take here the tangent, it has exactly the same slope. So this is the first order derivative. However, in A, the steepness, sorry, not the steepness, but the speed of how the gradient changes is much larger, right? Because if I delete this, sorry. Because here the gradient has a value of A, and after we take a small step to the left, the gradient has a value of 0. So from A, we go to 0. So the speed of change of the gradient from dl of dw at time step 0 is a, whereas here the same gradient at time 1 is 0. So there is a very abrupt change. In this case, however, in B, after a small change here, the gradient does not become 0. It becomes something from A becomes something like A over 2, like half A, something like that. So the change is actually much smaller from A to half A. So in that case, we use the inverse Hessian to adapt the learning rates per dimension. However, the problem is that the inverse of Hessian, the Hessian is actually quite expensive to begin with, but also the inverse of Hessians is very expensive. It has like, I think, a cubic complexity. And the fact that we have so many parameters in our neural network models does not help computing that inverse. Approximating the Hessian is a choice, is an option, perhaps using the LBFGS algorithm. It keeps memory of gradients to approximate the inverse Hessian, and it works okay with gradient descent, but with SGD, for as much as I've read, there is no reliable solution. In practice, SGD with momentum works just fine quite often, instead of having second order approximation of, instead of having second order optimization methods. So what is SGD with momentum? Basically, the intuition is that we make sure that we do not make very big changes in our gradients from one step to the other. We don't switch direction. We don't update our direction all the time. Instead, we're trying to maintain the momentum towards which we take our gradients. And it can be shown that it's actually this dampens oscillations. Basically, the SGD with momentum is similar to the SGD. So given our current parameter vector, we update it with a vector u, an intermediate vector u. Now the intermediate vector u, this buffer, is equal to a reweighted version of the buffer from the previous step minus a rescaled version of the gradient. Now, why this makes a difference? Well, this makes a difference because for oscillating directions, these ut plus 1 and gt actually cancel each other out. What do I mean by that? Think in this example that we have, this is the g1, right, for the first parameter vector, and this is g2, or let me call it gx and gy to keep it clear. Now, if we in this example, like let's check out this example, we take u1, u2, and u3 according to this algorithm. Now, if we replace g1 with gx plus gy, good. Basically, we haven't done anything yet. And now g1 is again here gx plus gy, whereas g2 here is gx2 minus gy approximately, right? Because here this is minus gy. So at time step 1 and at time step 2, the gy gradients are actually opposite to each other. So let me gy2. Let me write this a bit more clear. So gx1 plus gy1, which is basically also here gx1 plus gy1. Here g2 is gx2 plus gy2. Now we know that gy1 is approximately the same, but in the negative direction of gy2, right, by the geometry of the ravine. So here, this is like, we use the ravine as a motivating example, like SGD momentum helps with ravines. Now, because the jy1 and jy2 are opposite, they cancel each other out, and we maintain only the gradient towards the non-oscillating direction. So the SGD with momentum can actually help dampen oscillations. These are only approximations. In reality, gy1 is not exactly the same as gy2, like negative minus gy2. It's usually with some like rescaled version, but it doesn't matter, right? Because it's almost equal in magnitude. The gradient in the respective direction actually becomes much smaller. Now this, right, and what is even more interesting that is that, you know, this is happens time after time. So the influence of previous time steps get less important over time, exponentially less important. However, we do maintain some memory of our previous steps. So the exponential averaging cancels out the oscillating gradients. It gives more weight to recent updates. That's actually desirable. It leads to more robust gradient learning and faster convergence. In practice, values of gamma equal to 0.5 is usual, and quite often we want to anneal to higher values like 0.9. This makes sense because when your gamma is higher, it means that you want to maintain stronger momentum. This is logical because, you know, you're towards better convergence, like you're near your solution, so you want to maintain your direction. You don't want to change all the time. And in the beginning, changing more, so trusting more the actual local gradient, that's okay, because for one, our solution is not you know, necessarily great, so we want to take some a random guess, more of a random guess, but also it helps better with exploration, so we want to explore the local loss surface. RMS-prop is another algorithm that helps with optimization a lot, with you know, the pathologies in our optimizations. Again, the update rule is similar to the SGD. Given our current parameter vector, we update with the vector u. Now in this case, however, the vector u is basically the gradient itself, right? So it's exactly the same gradient, but rescaled per dimension. And what are the rescaling factors look like? They're basically approximately equal to the inverse square root of the gradient's history. What does this mean? That it means that if you know, historically we had very large gradients, when we take the inverse square root, or well, let's keep it simple. When we take the square root, the large values get attenuated, they get suppressed. So, you know, with a large value here, we go to a smaller value, like with a square rooting. And vice versa, when we have small gradients historically, then they get lifted to a higher value. This means that with RMS-prop, gradient dimensions that in the previous time steps were too large, so too aggressive perhaps, they get tamed, they get suppressed, whereas dimensions that were too low-key, they get boosted. So this sort of performs simulated annealing, and it helps a lot. So it helps a lot in this case of the ravine, because you know, in this case, this let me use a different color so it's more visible. Here, these gradients are large, right? The gradients that are perpendicular to the steep part of the ravine, they are large, so they get suppressed here. Whereas these small gradients, the dimensions of the small gradients that were small but relevant for us, they obtain larger importance. Another very popular, perhaps the most popular optimizer out there is Adam, actually invented in the, from Dirk Kingbuck from the University of Amsterdam. It's one of the most popular learning algorithms, and it's basically a combination of RMSProp. So it has the adaptive learning rate of RMSProp. Now we can see it here. But also uses momentum terms. So it uses past information to update per dimension the learning rate, and also it uses some correction bias. So Adam actually works really well. It's the go-to choice for in many cases. Another variant is another optimizer. Sorry, is Adegrat with a scheduling system, of again of the learning rate of the gradient. It's quite similar to RMSProp. Now the denominator is equal to the sum of the squared gradients of the loss with respect to parameters. So gradients become gradually smaller and smaller. However, there is no exponentiation here. And well, no, there is. And Nesterov momentum. So Nesterov momentum uses the future gradient instead of the current gradient, and so it takes a half step into the future, and it yields better theoretical convergence. It generally works well with convolutional neural networks. Now, as a visual overview, now I cannot really show it online, but if you check this link, you can actually compare the different optimizers, and you will see that Adam does a great job. Stochastic gradient descent does also pretty good with momentum. In practice, stochastic gradient descent works quite alright for many cases, and for more complex models, Adam is often the preferred choice because it allows for adaptive learning rates, so that's actually quite useful. However, Adam tends to over-optimize. So quite often, your data is going to be noisy. You might have some shift between the training and the test set, and Adam finds very good local optima, local minima, which, however, do not generalize that well. So if you have a weird landscape, if you have a weird loss surface, it might be better. You might be better off if you go with SGD with momentum. Thank you.